A thin flexible wire of length L is connected to two adjacent fixed points and carries a current I in the clockwise direction, as shown in the figure. When the system is put in a uniform magnetic field of strength B going into the plane of the paper, the wire takes the shape of a circle. The tension in the wire is IBL upon pi, IBL upon 2 pi, and IBL upon 4 pi. Okay. Now look, the length of the wire is L. So what will be the radius? Radius will be circumference upon 2 pi. Okay, the radius of that wire will be circumference upon 2 pi. Now, because of the circular symmetry, we can imagine any particular element, length element of that particular wire. Okay, so let us suppose this is a length element. Okay, suppose this is the length element dl. Okay, and let us say that the current is flowing in this direction. Okay, let us suppose that the current is flowing in this direction. Okay, so the most convenient one to imagine is this one, right? The one at the top. Okay. Now, what will be, or rather in which direction will the magnetic force be? Can you tell me? Let's call it df bar. I dl bar cross b bar. Okay. Now look, I dl bar is leftwards, towards right, towards right. Because that is along the tangent. That is along the tangent. What about the field? Field is towards the screen. Okay, so this time I'm doing it right. It's cross, which means the field is going into. So the middle finger, the index finger of your left hand should be pointing towards the screen. The middle finger of your left hand should be pointing towards right. And where is the thumb pointing? The thumb is pointing upwards. The thumb is pointing upwards. Okay, thumb is pointing upwards. So have you understood till this? Okay, but look, this direction of this force is actually going to be radial, right? Here it is in this direction, here it is in this direction, here it is in this direction, and so on. Now, if that force is radial, why is it? Look, now it's taking the it's taking the circular loop. It's pulling it from all directions. Okay, I mean, and that's why it has attained the shape of a circle. Okay. Now, if we consider the loop as a whole, then you can think of those df bars cancelling each other. But if you think about a single portion, okay, if you think about a single portion here, then df bar needs to be balanced because the loop is in equilibrium. Therefore, every part of it should also be in equilibrium. Okay. So what? How are we going to now proceed? Look, tension is always along the tangent, right? So let us show the, oh, sorry. Yeah. Suppose the tension is like this. Okay, suppose this is the tension. Okay, and suppose that this particular circular arc subtends an angle d theta at the center. Okay, suppose this loop, it subtends an angle d theta at the center. Okay, d theta at the center. So can I say that this angle is d theta by 2? Yes, I can say that that angle is d theta by 2. Now, Suppose we wish to determine the angle that this tangent or this tension along the tangent vector makes with the horizontal, that angle will also be d theta by 2. While solving mechanics problems, I have told you a fact. That is, angle between any two lines is angle between their perpendiculars. So angle between vertical and radius will be the angle between horizontal and tangent. Okay. Now look, for both the components, okay, horizontal components cancel each other. But vertical components counter df. Okay, vertical components will counter df bar because the vertical components of the blue vectors will be downwards, forces upwards. Okay, so what can I write then? Df bar is equal to, if the horizontal is cos, then the vertical has to be sine. So that would be 2 times t bar, if you say 2 times d bar sine d theta by 2. Raise your hands if you understand till this. Okay. So I can drop the vector notation now and I can say df is equal to 2t sine d theta by 2. And now we will bring that famous approximation that if theta tends to 0, sine theta tends to theta. And using it I can say that df is approximately equal to 2t sine d theta by 2, or that's just 2t d theta by 2, right? Okay. But what is that d theta? Okay, df is approximately t d theta. But what is d theta? Now look, arc length, the formula for arc length of a circle is what? Radius into angle, isn't it? It is radius into angle, correct? Okay, so what would that be? That d theta? That d theta would be arc length upon radius. Arc length is L. Or rather, wait, let's keep d theta there. Wait. Let's keep d theta. Let's go to df actually. Yeah, okay. I think that will be easier. Df is equal to I dlb. Sorry. I dl b is approximately t d theta because we want tension, right? Yeah, okay. And now we can think of arc length is equal to radius into angle. Okay. dl is arc length. Radius is L upon 2 pi. L upon 2 pi. D theta b, that is equal to t d theta. D theta gets cancelled, and then we can say therefore t is equal to bli upon 2 pi, or idl upon 2 pi. Upon 2 pi only one option is there, that is option C.